Okay, so our next speaker is Andrew Ilyas. Um, Andrew's currently an assistant professor at CMU, and I was really glad to have be in the same group as him during my PhD as well. So um, it's been great knowing him for many years, and he'll be talking about predictive models for AI training.
All right. Yeah, thank you, Noah, for the introduction. My name's Andrew. I'll hopefully define what predictive models for AI training are over the next couple slides. And I know we're starting a couple of minutes late, but the good news is that I think the beautiful tutorial to start this workshop off did a lot of the motivating for me, so I'll go pretty quickly through the motivation slides. Before I get started, I just wanted to thank an amazing set of collaborators who are now across like MIT, Google, Stanford, OpenAI, and I think Jane Street. Without whom this work would not happen at all. So thanks. Okay, so again, the high-level motivation behind this talk is what I called predictive models for AI training. And the dream here, the super high-level idea, is what if we could answer, without ever training a model, how changing a given hyperparameter would change learning dynamics, or how adding a given data source to my training corpus would change my model behavior, or how changing from a transformer to some other architecture would change my model's biases and performance. And at a high level, these are all questions that are answered by predictive models for AI training. And so what I mean by predictive models is something that allows us to predict or simulate the outcome of training a model as a function of this like super high dimensional design space that we're operating in when we build AI models. And so again, not to stress the point too much, because I think Noah did a beautiful job during the tutorial, but without such predictive models, we're sort of left shooting in the dark. Like if we have a hypothesis that changing our training data will reduce my model's bias somehow, and I don't have a good predictive model around training data, then what I'm left doing, which is unfortunately a little bit of what actually happens now, is sort of guessing like, oh, maybe I should like try writing some nice stories about like my AI being less biased, and then like that'll do it. Or maybe I should like downweight 4chan, which is probably not a great source for my AI being less biased. And I'm essentially just left like shooting in the dark. And this shooting in the dark is not only expensive, but sometimes it's just intractable, right? Like Alan was saying, when pre-training takes you 6 to 8 months, you can't really afford to like pre-train a couple of times with a couple of different data sets and see what happens. Okay. And so that's sort of the motivation behind building predictive models. They're meant to be sort of simple things that we can run and evaluate that give us reasonable approximations to model training and allow us to extrapolate behavior in a way that lets us more intentionally design AI models. So that's what we're going to be talking about today. And before I get started, I just wanted to note that sort of as a theory and ML community, we are making pretty good progress on developing these sorts of predictive models. So the canonical example of this, which is something Alan talked about, is scaling laws, which essentially allow us to predict a very coarse notion of model performance, in this case, like your sort of average loss on a big held out validation set, as a function of the amount of data and the amount of compute that I throw at training. And so you can view that as sort of like a very simple version of a predictive model. And then sort of on the other end of a spectrum, in terms of granularity, there's this emergent line of work in optimization theory that's about trying to predict like the actual training dynamics or learning dynamics as a function of which optimizer you choose. And there's a bunch of stuff in between along the spectrum, some of which is by the organizers of this workshop that I hope we'll learn about soon, and across machine learning. But I guess just to calibrate you, even though there's a bunch of work on this, I think we're still in the very, very early days of building predictive models for AI training, and it's by no means a solved problem. And just in the context of training data, which is what I'm going to be focusing on for this talk, there have been like order of magnitude improvements in making predictive models year upon year for like the last 5 years, and I think we're still nowhere particularly close. Okay. So that's what I'm going to be talking about today. I'm going to focus on this question of training data and trying to build predictive models for training data, which we're just going to define as like being able to simulate or predict the outcome of model training as a function of the design decisions that we make surrounding training data. I'll talk about an application of this to both data generation in the positive side and data poisoning in the negative side. And then I will talk about some open theoretical questions where I think, like so far, all of the things I will be talking about, there's no like really beautiful deep theory, but there are two areas where I really think there should be more beautiful deep theory, and we just don't have it yet. Cool. So we now get started, and like I said, the focus of today's talk is going to be making decisions about data. This isn't really like a necessary limitation to make. It's just that all the experiments I'm going to show you and all of the applications I'm going to show you are data related. So we're just going to focus on data, as people have said, data is kind of seen as one of the most important levers right now to pull when training machine learning models. So hopefully this isn't too restrictive. And questions, so like things to keep in mind, applications to keep in mind as we sort of try to build predictive models for data. We would like to build frameworks that let us answer questions like, can we design targeted changes to training data that induce a particular behavior from my model? Or can I, given a trained model, simulate a model that is like it but has never been trained on a given user's data, and like provide that user with some unlearning guarantees? Or sort of like in a pricing setting, can I estimate the contribution of a given participant to the performance of a machine learning model and use that to compensate them fairly? All of these are sort of questions that are answered by having a really efficient way to predict how will my machine learning model behave as a function of what data did I train it on. Cool. So with that, we can actually dive in. And I'm going to sort of frame the problem using this caricature of the machine learning pipeline that is much, much less detailed than the one we saw in the tutorial, but is going to be good enough for the purposes of this talk. Okay, my caricature of the machine learning pipeline looks something like this. As a machine learning practitioner, I pick a training data set, but the way that I pick this training data set is not by writing each and every individual document. It's often by making a much higher level decision. And I've represented that decision by W. So you can think of W as like the weights which I put on different data sources. You can think of W as like sample weights that I place on a bunch of documents. You can think of W as the parameters of a model that's going to generate synthetic data. The important thing is just that, is that important that we lost that screen? I can keep going, but.
Oh. Maybe let's try to fix that.
Okay. We have some redundancy.
We can see it on that screen.
Yeah. I feel like I'll just keep going, and then if we lose two, then we might need some intervention. Okay. Okay. The important thing about W is just that it's a high-level parameter that we pick that sort of determines what the determines what the training data is going to be. Okay. And then I'm going to define two functions. One of them is A, which is the learning algorithm, and A just takes this parameterization W and maps it to a trained model. And so you should think of A as encapsulating every aspect of a machine learning algorithm, like what architecture I'm going to use, what hyperparameters I'm going to use, how long I'm going to train for, everything. Even the random seed, I'm just going to wrap into A. Okay, so A is just a function that takes in W and returns a trained machine learning model. So you should think of theta here as being like a transformer. Okay, the second function I'm going to define is this evaluation function, phi. And that evaluation function is just going to take a machine learning model and return a real number. Okay, and that real number is up to the practitioner. It's whatever we're interested in predicting. So it could be like, if we were making scaling laws, then phi could be like my average loss on a held-up validation set. But phi could also be like my model's preference for Coke over Pepsi, or it could be its particular performance on a very narrow subpopulation. It really doesn't matter, as long as it's a function mapping a model to a single number. Question? Sorry?
Where do you put the data in this?
So the data is fully determined by W. So so you're saying the test data or the training?
The training data. You said W just got some parameterization.
Yeah, so the mapping from W, yeah, exactly. The mapping from W to the actual data set will be part of A. It's a great question. So I'm going to treat A as like the function mapping that parameterization to the model.
Yeah, so I think I also learned so what are the data parameterization?
Yeah, so W is just going to be, so imagine if I have like 10 sources of possible data, and the decision that I'm trying to make is sort of how much should I sample from each one, then W will be a vector in like R10, which specifies how much I'll sample from each data set. Or the example that we'll use on the next couple of slides is like, I might have, let's say, 1 million possible training data points that I could train on, and W will be like an indicator vector in like 0, 1 to the million that tells me which samples I'll include and which samples I'll exclude. But I've kept it purposefully abstract because we're going to consider a couple of different parameterizations. Okay, amazing. Any other questions about this slide? Because this is probably the most important slide, I guess. All right. Okay, so with this caricature in mind, the goal of building a predictive model, which when we started this line of work a while ago, we were calling a data model, is really just to build a predictor f hat that goes directly from this parameterization W to the outcome of training a model and evaluating it, ideally much faster than you actually would need to train a model and evaluate it. Okay, and there's like ways to make this formal, but I think for the purposes of this talk, we can just think about like we'll know it when we see it in terms of whether we have a good predictive model. Okay. Any questions about this so far? This is like the goal of this talk, I guess.
So the predictor only looks at the data?
The predictor will look at the training data parameterization and try to predict, without actually training a model, what would happen if I were to train a model and then evaluate that.
So this is a feasibility kind of thing? Does there exist a model?
No, so as soon as I pick a value of W, that value of W determines a model, like because I can just train on the resulting data.
It depends on A.
Yes,
A is fixed.
A is fixed.
fixed,
Yes,
okay.
A and phi are fixed here. Sorry.
Depends on A.
Okay, that's a great clarification. A and phi here are both fixed in advance. So given A and phi, I'm trying to design f hat.
So in your example where it's like you are taking samples, random samples with some so it can be randomized.
Yeah, so when A is randomized, just for simplicity, pretend that I take a random seed and I bake it into A. Okay. Cool. Any other questions about this? We can spend as long as on this slide as necessary, because the rest of the talk will be very underwhelming if you don't get this slide. Okay. Cool. So we'll start with a couple of basic ideas for trying to solve this problem. I think the most immediate idea that should come to mind, which is popular in a bunch of other fields outside of computer science where we try to build simulators, is just regression. Okay, because really what we're trying to build here is a simulator from W to some outcome. And so a natural first idea is to do the following thing. Let's take this f hat and make it like a parameterized function, parameterized by like some vector beta, which lives in like some latent space. We'll sample a bunch of data sets, or like data set representations, which map to data sets. For each of those data sets, we'll train a model and evaluate it. Right? And what this gives us is a bunch of covariates, which are just the data sets that I sampled, and a bunch of responses, which are what happened when I trained on that data set and evaluated. And so I can just regress one onto the other, and I end up with like some fit value of the parameter beta, and I can use this beta to then make predictions on new data sets. Okay, so to make this concrete, what we tried in when we first thought about this was just linear regression. So here, the data set representation that I'm going to fix is this like indicator vector representation. So I'm going to assume that I have a fixed pool of data, okay, and my representation of a data set is just an indicator vector of whether I included or did not include an example in my actual training set. Okay, so if my training set is like the first 100 examples of my pool, then my data set representation is like a giant vector that has 100 ones and then a bunch of zeros. Okay, and then I'll write down this parameterized predictor as just a linear function in this data set representation. Okay, so all I'm going to do here, based on the last slide, is just set up an intercept and then one coefficient per possible data point I could include. These betas, I can learn them via regression by sampling a bunch of data sets, evaluating the result, and then fitting beta accordingly. And I can then evaluate them on a bunch of held out data sets W. And I'm not going to spend too much time on this approach because even though it surprisingly works really, really well, despite the linear function being so simple, it's kind of prohibitively expensive to use in practice. Like the thing that I just described to you, I know Noah said, like, we should do theory, getting our hands dirty. This required getting our hands like really, really dirty. Like to actually fit these coefficients beta, we had to like build our own training training code that would let us train like 1 model per second. And then we trained like 100,000 models, and then we did this like weird L1 regression stuff. Doesn't matter. It works super well, but it's incredibly expensive to actually build this predictor F hat. Okay, so even though we might be satisfied with the result, we're not super satisfied with like how long it took us to get there. Okay, but we can sort of treat this as like a potential gold standard. Okay, and yeah, I guess since then, this same principle of just like, I mean, it's not like a crazy idea, right? When you're trying to simulate something, to just like sample a bunch and then build a regressor, has been used to build predictive models beyond data to like hyperparameters, data mixtures, and in-context learning. Arsen? Yeah.
Did you actually retrain it n times?
Yes.
Okay.
Yeah. So in this case, you retrain it O of n times. Yeah. In this case, like 5n actually, because there's a lot of noise in training. Yes.
When you say it works really well, so there is a predictability that linear function should suffice?
It's actually not obvious that a linear function should suffice. There's, but it like empirically turns out to, and there's been since some like nice theoretical papers about like why and when linear functions should be good enough. So it's not obvious that it should work, but it happens to work really well despite the expensive cost.
So
Yes.
is the goal to get like low error when, for example, you have a random W or something?
Yeah. Let's just say for now that the goal is like for new random W's that I didn't see, I want to have low error. Okay, and then this graph that I have here, where I say it works really well, is just like for a bunch of new random W's, sort of what my prediction of that evaluation function is versus what it actually was. Okay. Awesome. Okay, so that's idea number 1, and idea number 1 was great, but it was super duper expensive, and so a natural next question is whether we can do better than this in terms of the computational cost it takes us to actually build F hat. And a very enticing idea here is to use this really powerful tool from robust statistics called the influence function. And again, for the sake of time, I will not go through the derivation of this, but the high-level idea is that imagine if we were not doing AI anymore, if we were just doing statistics, if I had like a M estimator that minimizes some like strongly convex loss, and I assume a bunch of other stuff, then what the influence function gives me is a closed form that tells me exactly the effect of up or downweighting any given observation on the parameters of my estimator. Okay, so like imagine if I was like doing linear regression and I had like 1,000 samples, and I wanted to know like how would my like estimated coefficients change if I were to like up or downweight any given example by a little bit. It turns out that there's like this really beautiful closed form that tells me exactly how to compute this. Okay, so this kind of suggests that maybe we can use this to build a predictive model where my parameterization W is actually just like how much I up or downweight a given example, and I use the influence function to get the corresponding coefficients. And you can derive this yourself if you want. It's not that hard. But the high-level idea is just that we have this tool that we know works super well in statistics. If we're willing to make a bunch of assumptions, perhaps we can just port it over to like AI land, and things will just work out in the same way that we ported over SGD, and things kind of just worked out despite there being no real good reason for them to. Okay. And the answer to whether this works is it's complicated. So to draw you, I guess like a very conceptual picture, imagine if I were to place like predictive models on this XY grid, where the x-axis is the cost that it takes to build them, and the y-axis is like how accurately I'm able to predict model behavior. This green dot represents what we just did with regression, right, where it was like super expensive, and yet very, very accurate. If we try to just like apply the influence function to AI world, it will not work at all. So it'll be a lot faster because it's like now a single closed form instead of having to train, n equals 500,000 machine learning models. But we relied on a bunch of assumptions that don't actually hold. But since then, there's been a bunch of work that basically the central goal of this line of work is like to try to somehow bridge the assumptions that we need for the influence function to work with like what we actually have when we train models. And there's a lot of really, really beautiful work along this direction that I don't have time to talk about today, but would love to talk about offline. Okay, but sort of the only high-level takeaway here is what we're actually after is this top left corner, right? We want things which are very fast to run and are extremely accurate in predicting model behavior. So how do we get there? Okay, and so the remainder of this talk will be on one tool that I think will be useful for getting there, called the metagradient. And so to explain the metagradient, I'm going to bring back this caricaturish picture of machine learning training, where I just had like a W. The W defined a model theta, and then the theta defined some like real number via measurement. And recall that our goal was to build something which predicts phi from this first W. Okay. A metagradient is going to be the just the derivative of this final evaluation with respect to the training data parameterization. Okay, so just to like dig into this a little bit, one thing that should be that's kind of neat about this is if we could compute this, which I haven't yet told you that we can, it would immediately give us a good predictive model for any parameterization that we wanted, for any continuous parameterization that we wanted via a Taylor series, right? For any parameterization W that you pick some reference point, W0, and then your predictive model just becomes like whatever you evaluate once at W0, you evaluate this metagradient once at W0, and then you build a first order Taylor series. Okay, so this would be really nice. But computing it, I guess, is about as hard as you would expect, given how useful it would be, because it requires taking a gradient not just through a model. So like a gradient through a model we know how to do, that's just like backprop. But here we're actually taking a gradient through the training process, right? So like if we were thinking about what does this gradient represent, what it's asking is how would slightly changing my training parameterization propagate all the way through the training algorithm, through the evaluation, and change the final measurement that I'm taking. Okay, so it's not immediately obvious how to compute this. Are there any questions about at least the goal here? Yeah?
How does the metagradient differ from an influence function? Or is it? Oh.
Yes. Okay, so in fact, you can view the influence function as just a metagradient for a specific class of estimators, and where this training data parameterization is like per sample weights. And sort of the thing that's happening is that if you write down what this metagradient should be, like via the chain rule, it's going to be sort of the derivative of your like evaluation function with respect to your model times the derivative of your model with respect to your training data. And what the influence function is leveraging is that for a specific class of estimators, this second term actually has like a really nice closed form. Okay, and what we're finding, and like the central goal that we're trying to, the central thing that we're trying to get around is that for real life AI models, it doesn't seem like this closed form is doing a lot for us. And so the question we're trying to ask is whether there's another way to get at the same thing. Okay, that was a very useful question. Any others? Yes.
What's the key reason those statistics things don't extend to the real life AI? Is it like they assume loss is convex there or something?
Yeah, so to make, basically the derivation of this closed form relies on an application of the implicit function theorem, which basically means that you need your theta to not only be minimizing a strongly convex loss, but also actually attain the minimizer. And crucially, you also can't differentiate with respect to anything that doesn't actually change the loss landscape. Because what you're assuming is that your W defines some loss landscape with a unique minimizer, your theta finds that unique minimizer, and then you're basically looking at how changing the W changes the minimizer of that landscape. Yes?
So missing some, let's say you have the meta-advantage. Wouldn't you have to do some sort of upgrade in the optimum?
Sorry, can you repeat the question?
Let's say you have the meta gradient.
Yes.
Wouldn't you have to do some form of gradient descent or something to find the optimum?
Oh, yes, that's a great question. So like we can repeatedly apply it. Locally around some reference meta parameter, we would hope that it would be predictive the same way the gradient of a function is predictive.
And this would be more efficient than linear regression?
Yes, that's the goal. Like it's hard to overstate how expensive the linear regression thing actually is. It's like really, really expensive. Like even, I guess when we get to applications, the most intensive application requires applying the metagradient maybe like 20 or 30 times.
No, I understand what linear regression is possible, but I don't understand why this would be more efficient.
Okay, we'll get to that very soon. Okay. Any other questions? Awesome. Okay, so let's talk about how to actually calculate it because it's not obvious that you can do this efficiently. Okay, and our goal is going to be to calculate this exactly. So we're going to try to not make any assumptions about the shape of the estimator or its structure beyond just like differentiability and being trained with SGD. Okay, so our first idea is as follows. We have this great tool, which is computer-aided auto-differentiation, which is actually just how we train models in general, right? So for like any computer-defined function that you can write in PyTorch, you can call like dot backward, and PyTorch will like magically compute the gradient of this function for you. And the way that it does this is that while you're computing the function, it will basically break down that function into a bunch of very simple elementary operations for which it knows the derivative, and then on the backward pass, it will compose those derivatives via the chain rule to give you a gradient. Doing a forward pass through a model is a sequence of operations that we can take the gradient through, but also training is just another really, really long sequence of operations that we can maybe just take a gradient through. Okay, now the obvious problem with this is that, like I said, while you're computing this operation, your compute engine, in this case like PyTorch or whatever, needs to keep track of every operation that you did in order to store sort of the intermediate products necessary to compute its gradient. And so if you try to sort of like, let's say you were training like a really, really simple MNIST classifier or something, and you wanted to just write out the training loop and take a gradient, you'd need a GPU that has like 2 terabytes of VRAM or something like that, which is like a lot more than any existing GPU has. And that's for a really, really simple model. Okay, but so even though this is like a totally useless algorithm, it's useful for introducing this black box that I'm going to use a couple of times. That is computer-aided auto-differentiation, or backprop. Okay, so for the next couple of slides, just think of backprop as this magic black box, which takes in a compute graph that is like, goes from many variables to one variable, and can compute the gradient of this compute graph with O of edges in the compute graph memory, for some very loose version of O of edges. And the question is whether we can use this black box in a more intelligent way to actually compute the metagradient that we care about. Okay. So a second innovation here is to realize that even though trying to just call auto differentiation through an entire training loop was a bad idea, the structure of a training loop is actually not one of an arbitrary compute graph, right? Training is actually a very, very structured sequence of operations where I start at some state. I'm sorry, I changed Z for like Z here should be W, but I start at some state, and then the previous state and my data determine my next state, and then that state and my data determine the state after that, and so on and so on and so on. And so if I'm trying to take the gradient of this final thing with respect to these Z's over here, I can actually decompose this, and there's like a really nice dynamic programming algorithm that lets me write this only in terms of basically the derivatives at each step. So I can start at the end of this graph, I can take a derivative through a single step of model training, I can save that, I can go back a step, I can take the derivative through that step of model training, I can go back a step again, and so on. And at each step, I can sort of just recompute that single iteration of model training and take a gradient through it. And that's going to work a lot better. Okay, and so that leads to the following algorithm. I'll train my model once, And while I'm training that model, I will save every single state that I ever see while training. Okay, so I'll save the initialization, take a gradient step, save that, take another gradient step, save that, over and over and over again until I'm at the final state. Then when I want the metagradient, what I will do is I will loop backwards through these states, and at each state, I will compute the derivative of just that state, and basically manually propagate the derivative backwards all the way through training. Okay, so this is already going to be much better than direct auto differentiation because we can actually, this is like an implementable algorithm. Okay, the problem is that if you try to do this for, let's say, like a GPT-4 size model or even a GPT-3 size model, you quickly realize that like you cannot afford to save every single state that you ever touch to your disk because it just will not work. Okay, and so what we found is that there's a really simple modification to this that's also quite widely used elsewhere in computer science that in the context of taking the metagradient we call replay. And so the key realization is that the only primitive we needed from this stepwise auto differentiation algorithm was the ability to iterate through the steps in reverse order. Right? We just needed to be able to start at t and go back from t to 1, loading each state whenever we needed it. So what we can do is we can first make training deterministic. So this is a little bit complicated because like GPUs themselves are not deterministic, but if you try hard enough, you can get training to be totally deterministic. And when you do that, you can design the following algorithm. Rather than saving every single state, what I will do is, while I train, I will save every kth state. And then when I'm going backwards through the states, whenever I'm loading a state that I've already saved, I'll just load it. If I'm loading a state that I haven't saved, I'll hop back to whatever the most recent state that I've saved is. And then I'll retrain that segment, save all of those states, and then just iterate backwards through those. Okay, and so a pretty simple calculation here shows that we've gone from saving t states in memory to saving t over k plus k states in memory. So we've gotten our memory down to root t. Now, if we're training really big models, even root t, if we're training really big models, even root t is too big. And what we can do is actually just recurse this idea over and over and over again. Okay, so imagine I first basically train once and I save every 100th state. Then I instantiate this last segment, and within that last segment, I will save every 50th state, and then within the last segment of that, I'll save every 25th state, and so on. And what we can show, what's pretty easy to show, is that this is going to use log t memory at the cost of taking t log t extra training steps. And so this is actually going to make this practical even for very large models that we can't necessarily afford to save many copies of. Okay. I guess just a shout out to the TCS community, because I think this is the earliest instance of this algorithm that I could find, but there was a lot of work on reversible Turing machines, and essentially that's kind of what we're trying to build here. And so you can find the exact same algorithm in some old work on computational reversibility. And then I guess more recently, people have proposed this in the context of differentiating through actual models rather than training. Okay, so that's the algorithm. I guess if the last 3 slides were not clear, the high-level takeaway is just that we can now compute the metagradient, and we can compute it at a factor of a log t multiplicative factor on the cost of training, and extremely space efficiently. Okay, so in practice, this ends up being 5x as expensive as training, sometimes 10x if we need to be really aggressive with memory. Okay, but now, does this actually work? The good news is it actually seems to work really, really well. And so what I've shown here are graphs similar to the scatter plots I was showing you earlier, where each dot is a different data set. The x-axis of the dot is sort of what I predict will happen if I train on that data set and evaluate. And the y-axis is what happens when I actually do train on it and evaluate. If you remember, we had like a really nice clean line for the regression approach that's not shown here. The blue and the purple dots are these like influence-based methods, which tried to sort of bridge the gap between the assumptions we didn't have and the models we actually train. And the orange dots are what are yielded by the metagradient, which is both like an order of magnitude faster to run than these methods, and also seems to yield extremely accurate local predictions of model behavior. So this was like very surprising for me to see, because I was not sure that this was possible to predict. That's cool. Okay, this is just the same graph, except on the y-axis is the correlation coefficient from this graph as a function of how big the perturbation you're making to the data sets is. But again, the high-level takeaway is just that with a fraction of the computation, we're able to extremely accurately predict how model behavior is going to change as a function of the training data. Okay. Any questions about this before I move to an application? Yes.
So what's your kind of model for how the data changes? So should I think of it as like just one data point changes, like some random fraction, some adversarial fraction? So for which of those does this work?
That's a great question. Here, what we're showing are random fractions getting deleted. We also have results for adversarial fractions, and in the applications, hopefully, I will broaden our horizons beyond just random dropping of data points. I guess I can stay at this slide. Are there any other questions? Otherwise, I'll move to an application. Okay, cool. Okay, so the promise of all of this stuff, if you remember how I started my talk, was that if we build good predictive models for data, then we will be able to design data that elicits the behavior that we want from models, right? The whole point of building predictive models was to say, okay, if I want a specific behavior from my model, how do I get that by properly designing my data? And so the application I'm going to talk about is going to deal with this directly in the context of data editing. Okay, so we're going to assume that we have some fixed training data set, and what we are trying to do is modify that training data set in some way to elicit a target behavior from a given model. That target behavior could be a negative behavior, in the context of like data poisoning, or it could be a positive behavior if I'm like trying to teach the model something new that it's not good at via data synthesis. Ultimately, these are the same problem. I'm trying to design data that is going to change my model behavior in a targeted way. Okay, so let me start with a basic example, which is just data poisoning of a simple image classification data set. Okay, so the setup here is as follows. I have a big data set of like 50,000 samples, and I'm trying to insert a small number of poisoned samples such that when I train a model on those samples, the goal is for the model to just have bad accuracy. Okay, so in this case, I am the adversary, and I'm trying to see how bad can I make this model by changing only, let's say, like 2% or 1% of the data that it sees. Okay. The reason we chose this problem is that it's attracted a lot of work, both across like ML and TCS and differential privacy, because in the setting of what's called indiscriminate data poisoning, so this is slightly different from what Noah was talking about with backdoors, because here we're actually not allowed to change the inputs at test time, right? We're trying to make the model just like bad in general, rather than backdoored. And people have found that in this setting where you're just trying to make the model generally bad, data poisoning becomes much, much harder. And in particular, like for the class of models that we were studying, it was unclear whether like basically the state of the art was you could poison like an epsilon fraction of the data set and you could get like an epsilon percentage reduction in accuracy, which is like not super satisfying. Okay. So here is going to be our approach to poisoning data using this predictive model. We're going to change our data parameterization slightly from being sample weights or inclusion vectors or perturbations or any of that stuff. And our data parameterization in this case is actually going to be the individual pixels of a bunch of images. Right? So we're allowed to do this because we're the ones who pick the data parameterization. And our learning algorithm A is going to basically map this parameterization to a model by taking the images therein, adding them to a fixed training data set, training a model with a standard learning recipe. And then our output function that we're interested in evaluating is just like the validation loss of the resulting model, which we're trying to maximize. Okay, so what are we going to do? Well, we'll initialize W to just be like some clean examples. And repeatedly, we'll do the following. We'll train a model where we replace the first epsilon fraction with the Poisson data. We'll compute this metagradient, which again gives us this predictive model as a function of the pixels of the Poisson points. How do we think the validation loss is going to change? We'll take a gradient step, and then we'll just repeat this process over and over and over again. Because as there was a question earlier, like this predictive model is going to be locally predictive around some reference point, but maybe not good enough to be globally predictive. Okay, so this is all we're going to do. And here are the results. So in pink here is the accuracy of the original model. In orange is the accuracy induced by the best data poisoning method that we had at the time, poisoning flat 1% of examples. So we could reduce the accuracy by roughly 0.8%. And just by repeatedly applying the metagradient over and over and over again, we managed to lower the accuracy of the model by 14%. And just for fun, these are what the poisoned examples look like. They're kind of weird. Okay. And so this is to us, this is a big success, because what it showed is that by actually building a model of how we think the val loss is going to change as a function of the pixels, we were able to beat sort of any other method for building targeted data by an order of magnitude and a bit. Okay, I think I have 10 minutes. Is that roughly right? Okay, cool. That should be enough. Yeah, before I talk about I want to get to the open questions for theory, because I think they're super important. I briefly want to talk about some ongoing work on generalizing this to large language models, because a fair criticism of this is that you look at this and you're like, okay, this is CFAR 10, it's 2026, and in practice, there isn't such a clean map. An adversary can't exactly, edit the exact pixels being seen by a model anymore. Reality is much messier. And so if I'm the adversary, the realistic things I can actually do are I can sort of just put a bunch of things on the internet, or maybe I'm an adversarial data vendor and I can just sell you some bad data. And then, for me to really accomplish my goal as an adversary, I need to make sure that after you curate your data and after you filter it and after you tokenize it and do all of this stuff, whatever poison behavior I initially intended still survives all of this stuff and makes its way into your final model. And so there's been a bunch of work on this, not in the context of metagradients at all, that have shown really good promise in actually getting in actually poisoning or otherwise changing the behavior of large language models as a function of data. And I think without going too much into detail, an ongoing line of work that we're really excited about is that you can basically take any of these ideas, insert the metagradient inside as a predictive model, and use it to do slightly more efficient guided search, and then improve the performance of the method by an order of magnitude. So I'll actually skip data filtering, because I think the most natural thing that people do here is, for example, optimizing data generators. So the goal in this experiment is you have some teacher model that you're trying to train to generate malicious data, such that a student model trained on that data has some target behavior, expresses a preference for a given type of animal, or expresses preference to do malicious things or whatever. And so there are two relevant baselines here that people have looked at. One is this thing called subliminal learning, which is basically you train a model that has this desired capability that you care about, and then you generate data from that model, and kind of magically, a model that's trained on this data happens to share the same target behavior. And the second is reinforcement learning, which is where I start with just a base model, I generate data from it, I train a student model on it, and I use the exhibited preference of the student model as a reward to basically train my teacher model. And the high level idea here is that really what we're trying to solve is just a very complicated bi-level optimization problem, right? Like at the end of the day, what we're trying to do is we're trying to maximize with respect to the parameters of some teacher what will happen if I generate data from that teacher and then train and evaluate a student model on the generated data. And so to skip over a bunch of math, you basically get a lot of mileage from taking any of these methods and replacing this expensive student training that's in the loop with a predictive model that's derived from the metagradient. Okay, and just by doing this, sort of in the right way, you can greatly boost the performance of any of these methods. Okay. And then the result of this, which I don't have the graphs for yet, is that we can actually do real scale data poisoning on large language models. Okay. I'll skip past more applications of predictive models, but yes, you can do more things than just optimize data with predictive models. But where I really wanted to get to are what I think are really important open questions for where we're missing a lot of theory. And I'm going to focus on two of these questions. One is going to be this concept of meta-smoothness. So in order to explain this problem, I need to give you sort of a general caveat about this presentation, which is kind of an ugly detail that I elided while explaining, which is that if you try to take this metagradient algorithm that I described and apply it to a standard learning algorithm, you will get garbage. Like it will just spit out infinity and like minus infinity and nan, and it's like a disaster. And the reason for that is that if we think about sort of the landscape of the function that we're trying to predict as a function of our training parameterization, this is a real picture. It looks like this, right? And so even if you're able to perfectly compute the gradient of this function, it's like totally meaningless. It just like, it doesn't help you make any sort of meaningful predictions at all. And so for every single application that I showed you, and for all of these things, what we actually had to do is first come up with like given an algorithm, we have to come up with a nearby algorithm that is smooth in this way, right? And we can come up with like a pretty simple diagnostic for the smoothness of an algorithm. We then applied metagradients to the smooth version of the algorithm and then took whatever result we got and plugged it back into our non-smooth algorithm. So like there's no actual cheating happening, but it's extremely unsatisfying because like whenever you want to apply the metagradient, what actually has to happen is like you have to launch a giant grid search where you like the things to go from here to here involve like setting the learning rate properly, like not dividing by square roots, adding a bunch of like plus epsilons everywhere, adding a bunch of different types of normalization, and basically just like running a big grid search to find a configuration that happens to be smooth. And to me, this is like not a good thing. I guess to anyone, this is probably not a good thing. But I think that there's real potential here in the same way that we have theory for a lot of other aspects of learning dynamics to sort of try to build a theory of learning stability. Because we actually know exactly what operations are being carried out inside these networks. And you can even without doing too much math, reason about why some of these operations would not be amenable to metagradients. And so the hope is that with a little bit more effort, you could think about how to train models that are sort of stable and smooth a priori, rather than having to do a post hoc grid search to find good parameters. The second question I had, which I think will be answered at least partially by Sam's talk later this week, is if you remember our regression approach, which I'll just put here because it was a while ago now, what we did is we sampled a bunch of data sets, we evaluated the output that we cared about for each data set, and then we fit a regression sort of from the data set we sampled to the output we measured. And we said that this was prohibitively slow, super expensive. Okay, but one advantage that's sort of not to be discounted is the fact that the cost here is actually amortized over as many evaluation functions as I cared about. Right? So if you think about what's expensive between the learning algorithm and just the evaluation function, the learning algorithm is the thing that's really, really expensive. And so even though I'm paying for a bunch of learning algorithms, if I ever wanted to change, like let's say I first built a predictive model for like whether my language model will prefer Coke over Pepsi, and then now I'm trying to build a predictive model for its loss on some subpopulation. With the metagradient, what I would have to do is basically start from scratch because I haven't saved any useful intermediate products for me to like go out and build a new predictive model. Versus with the regression approach, as long as I save those like, hundreds of thousands of models that I trained to begin with, if anyone comes to me with a new evaluation function, I just have to like very cheaply evaluate all of those trained models that I've saved. And so I think a really interesting theoretical question that I think Sam's talk will make some progress on Wednesday is whether we can combine this idea of amortization of cost across many runs with sort of like the efficiency and accuracy of metagradient computation. Cool. So I think I'm just about at time. The big takeaways from this talk are just that I think predictive models for AI training are worth working on. They will help us make better training decisions, hopefully anticipate model behaviors before they happen, and a bunch more applications that I'm happy to talk about offline. And if you have any questions, there we go. My email is on the slide, and most of the papers that I talked about are online. So thanks so much.
Any questions?
Yeah.
So kind of related to the second question about generalizing over different trustworthy or like safety somewhere. There are also these surprising observations like, in ML, like unexpectedly, if you average models, somehow it just works. The kind of thing where things seems to be a little bit universal. Has there been any work on trying to come up with more universal predictive models that if I go from GPT 5.5 to 5.6, I don't have to pay the training again and I can still make some rough predictions?
I think it's a super important problem. There's been a little bit of empirical work, and it's been, I think people would be very supportive of more theory and also even like more fine-grained empirical work. Like as far as I can tell, the empirical work has mostly been of the flavor that like, if the models are kind of the same, then the data for them will also be kind of the same. But you would hope to say something more fine-grained than that. It's a great question. Oh, should I be repeating the questions also? Okay, the question was whether there's been work on some kind of transferability or universality of predictive models across model classes. I will try to repeat questions.
So, here's a basic question. What does the model stand for in predictive models?
Oh, like why is it called a predictive model?
Yeah.
Oh,
What does the model stand for? Does it stand for A or predictive?
that's a great question. I'm calling the predictive model F hat because it is like you can think of it as like a conceptual model or a toy model for the whole training pipeline. So it's model not in the, there could be a better word for it, but it's model not in the sense of like LLM, but in the sense of like, like I don't know, some kind of physics model.
Predictive model for different models, you mean?
So like, oh, sorry. Okay, so a predictive model is a single thing, which is like this function f hat. And then the question was about for different learning algorithms, basically. So if I change the learning algorithm from something like GPT-5 to something like GPT 5.1, can I have a single predictive model that will simulate the output of both learning algorithms? Yes, and then one back there.
Or maybe that one first.
It was kind of a related question. Like in the context of data poisoning, we want something that will work even if we don't know it.
Yeah, absolutely.
So I think a lot of what you talked about predicated on parameterizations that were continuous, and like a lot of questions that you were interested in were like architecture and things like that. Presumably, at least not directly continuous. Like, do you have thoughts on how it might apply?
Yeah. I think there's two broad ways that it might apply. Let me go back to this guy. This guy. there's two broad ways in which it might apply. So one is that you might just find some way to continuously parameterize the decision itself. Like for neural architecture search, people sometimes do like soft gating between different architectural components or things like that. One kind of interesting way is that you can combine predictive models with something like reinforcement learning if you're trying to optimize over discrete parameters. So for example, like if you can come up with some distribution over those discrete parameters, then sort of like somewhere in this training pipeline, things have to become continuous because like eventually there will be embeddings of the language model, and then from there everything is continuous. So you can sort of hope to use reinforcement learning to optimize over this first discrete to continuous thing, and then build a predictive model over just the continuous to the final output. Yeah.
Wait, in the slide about meta-smoothness and the problems there, is your concern more the non-smoothness of the training algorithm A or phi itself or both?
It's likely both. It's mostly A, I would say. Like phi is usually, even when phi is an extremely simple function, like if phi is just reading off a parameter of the final model, usually there's a lot of non-smoothness in the algorithm A. And this could be like things as simple as like when you're optimizing things with an adaptive optimizer like Atom, there's a bunch of, like inside the algorithm A, there's things of the form like take the parameter and then divide by like the square root of something. And then if you're taking a derivative through that again, then like that will almost certainly explode. And so you have to sort of like add plus epsilons in a lot of places to get from here to here. But that's just one of the things that you have to do. And it's like necessary, but not sufficient.
Any last questions? Let's thank Andrew again.
Okay.